Now this question is a fairly straightforward one, but again you have to give a complete answer. We're being asked to look at the trends in atoms and ion sizes and give an explanation. So first of all we've got to identify what those sizes are, and if we look at the bold numbers, they're the ionic radii. So the ones in yellow that I've highlighted, they're the ones for the atomic radius. So you need to consider not just going across a period but also down groups and how that changes. Now going across this first row, and if you look at the subsequent rows as well, for instance one below it with sodium going across, we get the same pattern as we go there. As we go across rows in the periodic table, we're in the same energy level. We're adding more protons, and as we add more protons as we go across, it's going to increase the strength of the electrostatic attraction for the outer electrons, and that's going to mean the radius will get smaller as we go across, and we see that as a pattern. Now then, if we look going down a group, and this is true for all groups, as we go across we can make a comparison that as we go down we're getting an increase in the number of protons, which should increase the nuclear charge, and it does, but we're also getting further away. The distance is further, we're increasing electron shielding, and that's obviously a big significant factor, and that means we're going to get less electrostatic attraction, so the radius is going to get bigger. So we need to kind of talk about some of those factors when we do that. Now the ions is a little bit trickier. We really need to talk about cations and anions a little differently. I mean, we've got, this is the ionic radius as we go across, and as we see it's getting smaller as we go across there. We're getting we've got less electrons, so we've got less electron repulsion, and one thing you should make a comment on is that sodium, magnesium 2+, and aluminium 3+, they all have the same number of electrons. So the only thing that's really changing between them is the number of protons. So the nuclear charge has increased, and that means you're going to get a greater electrostatic attraction as you go across. So you would expect the atomic radius, the ionic radius, to decrease as you go across. So you need to explain that. You need to specify that they've got the same number of electrons, and the only thing that's really changing is the number of protons and nuclear charge, which obviously affects the attraction, the electrostatic attraction. Now when we look at the anions, and we can look at different rows, we've got more electron repulsion, and that means the radius is going to be bigger than the atomic radius, and we've got the same number of electrons in this period, so they're isoelectronic, and the only thing that's really changing as we go across here again is the number of protons. So we've got, even though we've got more electron repulsion, which makes them bigger than the atomic radius, as we go across we get more nuclear charge, which means we're going to get a stronger attraction. So we would expect as we go across for the ionic radius to get smaller, which it does. Okay, and if we do a good job of talking about that, we should be able to get full marks for that. Now the most basic thing obviously you need to talk about is how the size of the cation, for instance, changes compared to the size of the atom. So the most significant factor for this, so for sodium, going from sodium to sodium plus, is really the loss of an energy level, and that means there's a significant change in the distance, there's less electron shielding, and so that's true for all the cations listed here. And the most significant factor for the anion is the addition of electrons, which means extra electron repulsion. So you've got to bring out those significant factors in your answer. Now I'm just going to attach a copy of the mark schedule because that does a reasonable job of explaining this. And here it is. Obviously you can download that and have a look at it at your leisure.